but it kind of depends on how quickly we progress through the ether chapter. So let's hold off on this for now. Okay, so I think the last time, actually before we get started, does anybody have questions or on scheduling or content or anything like that? Okay, then why don't we go ahead and get started. So the last thing that we were talking about prior to the exam was mass spectrometry. And before we get too far into this, go ahead and record. Okay, so the last thing we were talking about was mass spectrometry, and we had all but finished it. We had finished going through all the functional groups and talking about all of the predicted fragmentation patterns for each of the functional groups. So we had finished up talking about the carbonyls, and I just wanted to look at that one final example of a carbonyl mass spectrum so that we can see if we can identify some of the predicted carbonyl fragments. So that molecule is this guy here, the 3-methylheptane 3-one. So let me go ahead and draw that up here. Okay, so when we're looking at this, remember, as soon as the high energy beam of electrons hits a molecule, you're going to lose the electron that's least tightly held. So in this case, with the carbonyl compounds, you have 3 different types of electrons. You've got the electrons of the sigma bonds, you've got the electrons of the pi bond, and you have the lone pair electrons. And of those 3, it is the lone pair that are least tightly held. So you'll end up getting a molecular ion that looks something like that. And from here, we can go through and see about those expected fragmentations. So we talked about this last time. And like any of the functional groups containing a heteroatom, the carbonyls can undergo the alpha cleavage patterns, which means you cleave simply on either side of the carbonyl. So you could cleave to the right, like that. And if we cleave in that style, we would end up with a fragment that looks like that. And the radical, in this case, would look like that. All right. We could cleave on the other side, in which case we get a radical like so, and the observable would be that. All right. What we said we could also do with these is these carbonyl, or these alpha cleavage patterns, can undergo sometimes rather prominent secondary fragmentations, where the carbonyl containing fragment is simply going to lose a neutral small molecule of carbon monoxide. So if we think about that, I'm just going to extend these a little bit further. So let's say, draw it this way, where we lost carbon monoxide from that fragment, and that's going to end up leaving simply a 2-carbon cation. So what I did there was I took this carbonyl fragment. If you cut off carbon monoxide from that, all you're left with is a 2-carbon cation. Okay? And then if you do that same thing to the red one, we lose carbon monoxide there. What that'll leave us with would be that as a fragment. Okay? Any questions about those fragments? All right, so let's go ahead and put some numbers to these real quick. I think we're dealing with a fragment that has a molecular ion of 128. And so if we start opening my calculator. All right, so if we take the first fragment, that first alpha cleavage pattern in blue, we have a total of 3 carbons, 36, plus 5 hydrogens, plus 16 for the oxygen. So this should have a 57 mass. Obviously the ethyl cation over on the far right is going to be a 29 mass. If you take the red, the 128 minus the ethyl radical, that's a 29, so that would be should be a 99 mass fragment. And then the other guy, that would be the 99 less the carbon monoxide, which 16, 12, 28, I think. And that, I believe, is a 71 fragment. The only thing we have not yet addressed with all of these 4 fragments is that one special rearrangement that carbonyls can sometimes undergo. That was known as the McLafferty rearrangement. So if we think about the molecule that we have, the ion that we have, would this carbonyl ion undergo a McLafferty rearrangement? Remember, there was that one requirement for a carbonyl compound to undergo McLafferty rearrangements. Not all of them will. So does this meet that requirement? Remember, that requirement was you've got to have at least 1 hydrogen in a gamma position. So if you look over here to the left of the carbonyl, all you got, so remember we just referenced the carbonyl and used the Greek alphabet to count away. So that would be an alpha position here, that would be a beta position there. So you cannot do a McLafferty from the left-hand side of the carbonyl, right? Put that in real quick. There's my alpha position, there's the beta, no McLafferty possible there. However, if you go to the right side of the carbonyl, you have alpha, you have beta, you actually have 2 gamma positions. So yes, from the right side of the carbonyl, you can do a McLafferty rearrangement. So let's see what that's going to look like. Okay, so remember, all of this begins with the carbonyl oxygen, the lone pair that is remaining on the oxygen, grabbing a hydrogen from the gamma position. So we could start with this. The electrons of that bond are going to go from the gamma carbon into the beta carbon. Like that. Well, you can't just make a new bond between beta and gamma without breaking an existing one, because otherwise the carbon would have 5 bonds on it. The beta carbon would have 5 bonds on it. So one of these existing bonds is going to have to break, and the one that breaks is the alpha beta. The electrons of that bond go into the carbonyl and ultimately back up on the oxygen. So if you follow this circuit of electron flow, I'll start with the right-hand part of the right-hand half of the molecule that got cleaved off. The right-hand part, you're actually not going to see, right? Because what you'll notice is that this is going to give us a neutral alkene. Draw these in explicitly. This is my gamma position. We said that we formed a double bond between gamma and beta. So we have that there. And then whatever else is attached. So this is the beta, and then you've got that ethyl group there. So there's my neutral alkene. And again, we don't see that because you only see charged particles. This is a neutral small molecule. You would not observe it in the mass spectrum. What we will see, however, is that would be my beta and alpha positions to the left. I now have the alpha position to the right that's double bonded. I now have a single bond to the oxygen, and it is now bonded to a hydrogen. So that one is going to have a mass of, what have we got, 4 carbons, so that's 48, plus 1, 2, 3, 4, 5, 6, 7, 8 hydrogens, and the oxygen. And that gives me a fragment with a mass of 72. And again, I think we talked about this last time. You can always recognize the McLafferty fragment because they are an even massed fragment. That's very unusual in hydrocarbon type compounds. Unless there's a nitrogen present, you usually don't have prominent even massed peaks. All right? So let's go through and see what we can find in the actual spectrum. So 128 is our molecular ion. You can see you've got a fairly prominent molecular ion there at 128. The next peak that we were talking about was the 99 fragment. That would be right there. That corresponds to one of my alpha cleavage, right, the loss of that ethyl radical. The next one we were looking at is probably a 71, or 72 rather. So we can see we've got 2 of them very close together. There's the 72. Right next to it is the 71. That corresponds to both the McLafferty fragment here and that carbon monoxide loss there. And then I think the only one we really have left is that 57, which is right there. And you do have that 29 over here, but you know, lots of things have 29, lots of things have loss of ethyl. So. Okay, does anybody have questions on any of the mass spectrometry?
I have a question about so for the lab, we didn't know how to do a fragmentation for the benzene ring.
Yeah, we talked about fragmentation for benzene.
But that was different. Ours for fluorobenzene has 70.1. We didn't know how.
Don't worry about it. For the lab, I'm not really concerned with anything lower than 77. With benzene compounds in general, you don't really need to worry about the fragments under 77 because that would mean the benzene ring starting to crack apart, and that gets really messy and not terribly informative.
I spent like almost 3 hours.
You should have emailed me.
Oh, like searching.
Yeah, if you have questions like that, then send me an email. I would have told you don't worry about it. Yeah.
I just had a kind of quick question about the labs spec. So I noticed a lot of them, or a lot of the calculations I did to like give us fragments were like 1 or 2 off. I don't know if that was me that did that or maybe like.
Well, sometimes it could be a number of things. It could be that the instrument was slightly out of calibration. That could be an issue. Alternatively, it can be the difference of a hydrogen. So, especially like, you know, for instance, if you have a benzene ring, you know, I told you whenever we were looking at these guys, if you have the fragmentation of a mono substituted ring and you lose the side chain, you should see that 77 fragment. If you have a di substituted though, it's going to be a 76. So it can be an instrument calibration thing, or it could just be the difference of like a hydrogen because of differential branching. So, okay. Any other questions on mass spec?
Professor, can you scroll through?
Oh, yeah.
So, the one that has 99 list number, that one can go through the faculty rearrangements, right?
Well, you're not gonna typically see a McLafferty rearrangement of a fragment. You know, this is already fragmented, so it's not gonna really undergo McLafferty rearrangement here. You typically will only see that on the molecular ion.
Okay. And then for it to actually go to battery, right, the oxygen needs to be electron, right?
Well, the oxygen of a carbonyl will always be able to undergo McLafferty because the only requirement on the oxygen is that it have a lone pair. And normally, when you ionize a carbonyl compound, you're losing one electron from one of the lone pairs, which leaves you always the other lone pair that would be available to do the McLafferty rearrangement. So just a quick note on the type of problems that you can expect to see on exams and things. You're never going to get a mass spectrum and be asked, what is this compound? Okay, there's just not enough information there. Kind of like you were never given an IR spectrum and said, what is the compound based on this IR spectrum? You just don't have enough information. So you, at most, I would maybe give you a mass spec combined with some other type of spectrum. That would be probably the hardest type of problem you would see. But most of the problems you're going to get are going to be things like, here's a compound. There's a noticeable peak at, say, 57 AMU. What is this peak from? And so basically what you're going to need to know are, what are the common fragmentation patterns for each functional group? All right, that's the main thing I want you to know from this. Okay? All right, so why don't we go ahead and move on. So that gets us through the first of 3 chapters for Unit 2. What we're going to move into now are the ethers. And I think once we start getting into these functional groups, you'll start to recognize a pattern that is very similar to what you saw at the end of last semester. Meaning that we start a functional group, we'll talk about nomenclature, we'll talk about physical properties, we'll talk about synthesis, and then we'll look at the reactions of. And then we're just going to repeat that functional group by functional group by functional group. So very similar to what you did last semester with the alkenes, alkynes, and alcohols. So as we begin ethers, we're going to start with how we can name them. Okay? So when we talk about an ether, we're talking about a structure something like this. So basically, it's alkyl groups that flank an oxygen atom. All right? And depending on the complexity of the ether, we can name them in a couple of different ways. So if you have a very, very basic ether, we're going to simply name this as alkyl ether, right? Based on the 2 alkyl groups that are attached to the oxygen. So for instance, if we had something like that, you have a methyl group on one side, and anybody remember what we call a benzene ring as a substituent? Yeah, phenyl group on the other. So we could call that then methyl phenyl ether. Okay. Probably the most common of the ethers that you've worked with before would be this guy. All right, that's a very, very common lab solvent. And you'll notice that it's symmetric, but you know, we're not going to necessarily call this ethyl ether. Because you know in nomenclature, when you have more than one of the same substituent, you just use the Greek prefixes. So this would then simply be called diethyl ether. Okay? So pretty straightforward there. So let's talk about what happens if you have a more complex situation. Let's look at this one. So in this example, we obviously have an ether, but it's not going to really lend itself to that very simple style that we just talked about. And so in a case like this, what I would encourage you to do is have a look at that functional group priority list. If you look at that functional group priority list that is on Canvas, that some of you probably have in your possession, if you find ethers on that sheet, you'll notice that they are way at the bottom in something that's dubbed the subordinate groups. So you can kind of think of them as like the second-class citizens of the functional groups. So they don't factor into the primary functional groups. Right? So in a case like that, what you're going to do is find the next highest one. So in this case, all you've got going on is alkane stuff. So we're going to call this and name it like a regular alkane with this as a substituent. And the way we handle the ether groups as substituents is very easy. You know, if this were just a 2-carbon group, we call it obviously an ethyl group. To indicate that there's an oxygen present, all you do is add oxy at the end. So this ethyl group with an oxygen becomes an ethoxy group. So it simply becomes an ethoxy substituent. And you can do that with any carbon chain size, right? If it was 1 carbon, it would be a methoxy. A 3 would be propoxy, butoxy, etc. All right, so then when we come to name this, again, we're going to name it as an alkane. So I think the longest parent chain here is going to be a 1 straight across, 1, 2, 3, 4, 5, 6. Numbering the parent, we're probably going to start from the right on this one. So starting from the right, you get your first substituent at the 2 position. If we started from the left, your first substituent wouldn't be until the 3 position. Okay, so that's why we numbered it that way. And then just organize the substituents alphabetically. This would be a 2-bromo. For ethyl. Oop, no. Ethoxy would go first. So that would be a 3 ethoxy for ethyl, and then hexane. All right. Any questions on that one? All right, let's look at one that's a little bit more complicated.
I do have a question.
Oh, you go ahead.
What if the oxygen is in a different place in the substituent? Is it?
You mean if you had a more complicated substituent?
Well, I mean, what if the O were in this, not directly attached to the carbon? What if it was in a different place? Never mind. Let's just keep going. I'll figure it out later.
Yeah, we'll see a couple more examples of this with more complicated substituents, so that may address your question. But if not, we can talk about it. All right, so let's look at this one. So in this one, we have a clear high priority functional group, namely the alcohol. So we're going to want to number this parent so that the hydroxy substituent gets the lowest possible number. So numbering this one, we would start from the left. And I think go up like that. All right. So here, just organize the substituents in an alphabetical way. You've got two substituents, I think. So we would call this a 5 isopropoxy. Oh, no, 6, sorry. 6 isopropoxy, 5 methyl. It's a 6 carbon chain, so that'd be a hex. 3E, ene, 2-ol. Any questions on this one?
Can we number, so for 6, can we do the methyl for the 6, or no?
That would not be the best way of doing it, because you would not get as many substituents that way. Remember, if you have a tie, you want to choose the way that gives you the most number of substituents. Okay, so up to this point, we've only been dealing with fairly simple alkoxy substituents, right? The ethoxy, the isopropoxy. So what I want to look at with this last example is what happens if you've got a more complicated ether substituent, all right? So let's look at this guy. All right, so what we've got to do is we have to choose which half of this ether is going to be the parent. So what do you like better? Which of the two halves do you think should be our parent in this case? Yeah, probably the top half, right? Because that has the high priority functional group in it, number 1. It also has the most number of carbons, number 2. So we're going to choose this as our parent. The high priority functional group in that is going to be the alkene, so we're going to number the parent, so the double bond has the lowest number. So that'll be starting from the right. Which makes this thing a complex substituent. Now, if you were thinking about that, I'm going to name this in the newer style of the complex substituents. So we would start numbering this one over here. And imagine if this were, imagine that the oxygen were not there. The way you would handle that substituent if the oxygen were not present, it was just a regular old complex alkane substituent, is we would call it a 2-methyl pentan 3-il. Does that make sense? Everybody see that? So to indicate that there is an oxygen splitting the complex substituent from the parent, it's very, very simple. All we do is propoxy on the end. So then in terms of the naming, we're just gonna, like always, organize the couple substituents that you've got alphabetically. So we would start with the 7 methyl. The complex constituent is a carbon 4. And then this is an 8 carbon chain, so that would be an oct. 2 E. All right. Any questions on any of these nomenclature problems? Yeah.
What's the older style of naming the complex substituent?
Oh, the older style would be, let me erase those numbers. So in the older style, remember the point of attachment is always the one position. So we would start numbering it like this. So it would be a 1 ethyl methyl propoxy.
Can we use that?
Sure, yeah, I'm fine. Whatever style you like, whether it's the old style or the new style, I don't really care, as long as you do one of them correctly. Any other questions on any of these nomenclature questions?
Yeah, I want to go back to what Danielle was asking a minute ago on the first example, or complex example. Yeah, so I think, Danielle, you were saying like if that oxygen is like one up on the.
Yeah, we're just looking at a really specific situation where the oxygens are between the substituent and the chain.
Yeah. So like if like
So if the
O
oxygen is
was-
somewhere else, we don't know what to do about it.
Like if it was like right above where that 2 is on that carbon, or that substituent.
If it were in some other place on the substituent, I'm not really sure how to deal with it, but.
So like,
Like that with the methyl coming off there.
well, in this case, you would just consider it part of the parent. You would make that part of the parent, right? So we would number it.
What if you had the bromo like
At the 5
or at
or the 4?
the one to the
At the
right.
same spot it was before.
Yeah.
Like that? You would still consider it that as your parent, and you would just name that as a complex constituent. So it would be like a 1 bromoethyl substituent.
So the ether is going to take priority in that case as opposed to the.
Wait a second. 1, 2, 3, 4. Oh, no. Don't worry about that. You're not going to see it.
Okay.
Yeah.
How do you
Yeah.
name that one carbon between the.
Yeah. So you would end up numbering the parents so that the longer chain got the would be the parent, right? So, but yeah, don't worry. You're not going to see that. Okay. So now that we've talked about nomenclature, let's look a little bit about the physical properties of these guys. Oh yeah, go ahead.
There's one more, so the one that you just did right there.
Mhm.
So what if that, parent function was also on the bottom half as well, right? So would you just name it as like -7-methyl-4 or whatever?
Yeah, well, you would have to then, like, so you're saying if you had a double bond here as well?
No, I mean like if you just take that top, parent function,
Uh-huh.
and then you replace the bottom function with that top one, right? So it's basically identical on both sides, you just create like a
Oh,
circle.
yeah, I guess that's a weird one. Yeah, I think you would call it a di blah, 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 ether. Yeah, but y'all are coming up with some weird ones today. Yeah, you're not gonna see that though.
You have to be ready.
I'm not that mean, jeez. Okay, so let's look at the physical properties of these things. So if you're looking at an ether, we'll just use a very simple example to start. So dimethyl ether. If you were to think about what this looks like, the Lewis structure, our central atom would obviously be the oxygen, so we put that in the middle. So in terms of, let's think back to your VSEPR theory, in terms of electron group geometry, right, that means considering both lone pair and bonding group. What kind of electron group geometry does this have? Yep, it's got 4 total groups, 2 bonding groups, 2 lone pair groups. So that means in terms of its electron group geometry, it's going to be tetrahedral. But of course, that's not going to be the overall shape because it has lone pairs. So what would the shape of this be? Something that has 2 bonding groups and 2 lone pair groups.
First that was square planar,
Trigonal planar?
but also it's square. But
Oh, it's square.
It's called bent, isn't it?
Yeah, it's going to be bent.
That's right.
Right, it's really no different than water, right? You got oxygen in the middle and 2 bonding groups on the side, right? So in the same way that water is a bent-shaped molecule, the only thing that we've done is replace the hydrogens of water with alkyl groups. So it's going to be the exact same shape as water. The bond angles will be a little bit bigger because methyl alkyl groups are bigger than hydrogens. But in terms of its overall shape, it's going to be bent shaped just like water is. So when you come to thinking about its intermolecular forces, do we have London forces? Well, naturally, because everything has London forces. Is there a permanent dipole in the molecule? Yeah, I think so, right? Because that oxygen-carbon bond is a polar bond. Oxygen is much more electronegative than carbon, and so you have a dipole going that way, and you have a dipole going that way. Due to the shape of the molecule, because it's bent shape and not linear, those dipoles don't cancel out. So there is a net dipole in the molecule, and thus you will have dipole-dipole interactions as well. Can an ether hydrogen bond to itself? Well, you have hydrogens, you have an oxygen. But there is no hydrogen directly bonded to the oxygen. And that was the requirement, right? You had to have a hydrogen directly bonded to either nitrogen or oxygen in order to hydrogen bond. We do not have that here, and so there is no hydrogen bonding. I should say to itself. Because you can, if you put these in the presence of water, imagine you're doing an extraction. Ether is a very common lab solvent to do extractions with. If you have ether in the presence of water, the ether can act as a hydrogen bond acceptor. Okay, so it can be a hydrogen bond acceptor if it's with a hydrogen bond donor, but it cannot hydrogen bond with itself. And this has some practical implications. So normally when you think of mixing ethers and water, they don't mix. You know, you've done extractions with ether before. And if you put ether in water, you get two separate layers. But there is a slight amount of solubility, and that is because of this hydrogen bonding aspect. So the way you can prove that to yourself is no matter how careful you are with your extraction, you know, you bring the interface of the layers right down to the bottom of the sep funnel and really careful and cut it off right at the interface. It doesn't matter how careful you are. If you smell your water layer, it is always going to smell strongly of ether because there's always a little bit of ether dissolved in the water as a result of this hydrogen bonding. Okay. I'm going to give you kind of a series of molecules just for comparison's sake. So if you look at the three molecules that I've given you, each of them has one type of the intermolecular forces. So for instance, the alkane just has London. The ether has London and dipole-dipole, and then the alcohol has all three. And so as you could probably guess, that is going to have a significant impact of the boiling points on these things. So the one with just the London is going to have the lowest boiling point, about -1 Celsius. The one that has all three is going to be the highest boiling point, about 117. And then the one that has just the London and dipole-dipole is going to be somewhere in the middle, around 34. So ethers tend to have fairly low boiling points, most of them. And this, it's kind of funny, you never forget, in grad school, I went to UC Davis, and you all know that the valley summers can get quite hot. And we were up on the 4th floor of the chemistry building where the air conditioning didn't work particularly well. And so you have to be real careful when you are working with ether and making sure to keep it in the fume hood because, you know, you figure the boiling point is at 34. It could, on a hot day in the summer on the 4th floor of a building, it could easily get to be 25, 27 Celsius. You're getting really close to the boiling point of the solvent at that point, and so it becomes highly volatile. And so if you're not working in the fume hood, you can really get a face full of ether on a hot day, which is not always the best thing. I don't know if you know this, but diethyl ether was one of the first surgical anesthetics that was developed. And so, yeah, you knew when you were working too long out of the fume hood with this stuff because you got a pretty darn good buzz going. Not that I'm recommending that for the record, but okay. So let's go ahead and look at some synthesis. How can we make these ethers? So the first one that I'm going to give you is the way that ethers are made on the industrial scale. So the way they're made industrially is a very simple process. You take an alcohol and you heat it in the presence of acid. So what do you think that acid is going to do if you take alcohol and you throw in acid catalyst? What's the purpose of that? Yep. Protonate the oxygen. And what do we do by protonating the oxygen? What was the point of that? Yeah, anytime you're ever protonating an oxygen, it's always for the same purpose. It's to make a good leaving group. So now that you have a good leaving group, another molecule of oxygen can come in, or of alcohol, excuse me, can come in and do an SN2 reaction, simple displacement. So that's going to give us something that looks like this temporarily. And then all we have to do is, I'm just going to say minus H plus, we lose the proton that regenerates the acid catalyst. And what you're left with is the ether. Alright. So that's the way they make these when they are synthesizing them on a large scale. There are some limitations for this. What would happen if instead of trying to make diethyl ether, what if I was trying to make ethyl methyl ether? I guess we would probably do this. Can you see a problem with trying to do this chemistry? Well, it could, yeah, I mean, you could, either one of these oxygens could protonate.
Probably bond to itself.
Yeah, exactly. I mean, you would get some of this, but then you could get the methanol reacting with itself to make dimethyl ether. You could get the ethanol reacting with itself to get the diethyl ether. And so you'd have a mess. So this industrial synthesis is really only good if you're trying to make symmetric ethers. The other limitation to this is that it is an SN2 reaction, which means you're going to be limited by all of those normal SN2 constraints. You know, so what do you? Let's say we were trying to make the symmetric ether of that. Do you think that would work? First step would probably be the oxygen going in, grabbing the proton, generates a good leaving group. Would another one of these alcohols be able to come in and attack SN2 style here?
It's too sensitive.
Yes, that's a tertiary leaving group. You're never going to have an SN2 on that. You would end up making a lot of E1 product here. So you get a lot of elimination. So this really only works well for unhindered alcohols. All right. So I'm going to give you a much better way of doing this. You're probably not going to want to use this industrial method in your syntheses. A better way of handling this is what's known as the Williamson ether synthesis. And with the Williamson ether, you're still going to start with an alcohol. But you're going to treat it with a base this time. And the base that's usually used is either sodium hydride or just elemental sodium. But all that's going to do is deprotonate the hydroxyl group. So it's going to convert the alcohol into the alkoxide. And from here, you just throw in a good alkyl halide. And it proceeds through simple SN2 chemistry again. All right. Any questions on this mechanism? So this works a lot better than the industrial synthesis. It eliminates the first of those two problems. So as you can see through the example that I just gave you, you can use this to make unsymmetric ethers if you want to. There is still the limitation that it is an SN2 reaction. So sometimes you have to plan your syntheses around this. You know, for instance, what if we were trying to make this? There's a couple ways you could think about doing that. Anytime you're doing a Williamson ether, you've got to have an alcohol and an alkyl halide. So that generally is going to mean you've got two options to do any Williamson ether synthesis. So for this molecule, we could have broken that up as, there's my alcohol, there's my alkyl halide. Or switch it around. Alkyl halide, alcohol. Which of those do you like better? First one. Why is that?
Who does second one look better?
Because it's less hindered alcohol.
I mean, yeah, you're right. The alcohol is a little bit more hindered here than it is here. But what has a bigger effect on SN2 reactions? The leaving group? You've got a primary leaving group there, secondary leaving group here. Yeah, the leaving group has a much larger impact on SN2 chemistry than the nucleophile. I mean, the nucleophile does have an effect, but the leaving group has a much larger effect. So in fact, if you think about it, when you learned about SN2 chemistry, you probably learned that if you have a secondary halide, you tend to get mixtures, you tend to get competition. What was the SN2 mechanism always in competition with? Well, remember, you're treating this with a base to generate the alkoxide. Well, the alkoxide is a good nucleophile, yeah, which is what you want it to be, but it is also a strong base. So if you have a strong base and a secondary leaving group, what are you likely to get? What's that? Yeah, elimination. In fact, if you did this reaction, you would get roughly, well, you'd get your ether that you were trying to make, but only in about 15% yield. You get primarily E2 mechanism from this. So the bottom line is when you're trying to use the Williamson ether synthesis, you really only want to use it when you've got either a methyl halide or a primary halide. You don't want to go beyond that.
And that's for the Williamson ether, you said?
What's that?
For the Williamson ether?
Uh-huh. Yeah, for the Williamson ether, you really only want to ever use it when you have primary or methyl halides. Okay, so so basically what I'm saying then is the better method here would be to do that one, because it involves the use of the primary leaving group. All right, so what if we wanted to make this? So again, Williamson ether would mean you're always gonna have to make one half the alcohol, the other half is gonna have to be the halide. So you're always gonna give yourself two choices. So I guess in this case, we could pair them up like this. Or switch it around. Which of those two do you like?
It's neither of them are great, but the top
Yeah.
one's better.
Yeah, I would agree with that. But really, both of them are pretty awful. So, based on what we know about Williamson ether at this point, there's really no way you could use either one of these to get this ether in good yield. So what that tells us is we need a better method. Or not necessarily a better method, we just need another method, a complementary method. Williamson ether is great for making unhindered ethers. It's just not very good for making hindered ethers. So that's the third method I'm going to give you. The third method will be a good way. We'll come back to this. The third method is going to give us a way of making these very hindered ethers. And it's one that you already know. This is a reaction you at least know to some extent. This next reaction is what's called alkoxymercuration. Does that name ring a bell? Does it sound vaguely familiar? So you learned last semester that if you had an alkene, you could take and treat the alkene with that mercury salt, mercury 2 acetate, and water, in a reductive workup, and it was a way of putting OH groups onto double bonds. Now, was this the Markovnikov or the anti-Markovnikov edition? That's Markovnikov, right? Yeah, that did not have rearrangement, exactly. So you got that. So just really quickly, remember this goes through that mercurinium intermediate. But if you recall, we draw the intermediate this way with a formal charge on the mercury ion, but that positive charge is really kind of distributed through the three-membered ring. And it's gonna be more localized on the carbon position that's better able to handle it, meaning it's gonna be more localized on the more substituted carbon. So you could draw this kind of more accurately like that. And I've designated kind of that more substituted carbon position with a double positive, because it's a more substituted carbon. You can better stabilize the positive charge. And that's why when the water comes into attack, it attacks at that more positive carbon position. Okay. Y'all remember that? Anybody have questions about that? Okay, well, if we wanted an ether, what could we change?
We can use epoxy instead of the water.
Yeah, exactly. Use an alcohol, right? Instead of using water, if we used an alcohol, that should give us the ether. So now, instead of having an OH sticking off of the more substituted carbon, you're gonna have an OCH3. So we get an ether. And a fairly substituted, fairly sterically hindered ether at that. An ether that would have been difficult to make with Williamson ether synthesis. So let's go back to that problem we proposed a minute ago. I think it was something like this. So with this new reaction, with the alkoxymercuration in hand, could you figure out a way of making this now? So think about that for a minute. How could we get to that very hindered ether? Remember, one half is always going to be the alcohol, and the other half is going to have to be your alkene. So I think with this one, I would probably divide it up so that the isopropyl group was the alcohol, and then this top part, the alkene. Just because otherwise, you're gonna end up with a very, very hindered alcohol trying to be your nucleophile. So I think that's the better way of doing it. Which I guess one way of doing this then would be like that. Would that give us the right ether product? So the mercury would end up across the double bond, and then the alcohol would attack the more substituted position, which I think would give us, yeah, would give us the right ether. Is there any other way we could do this? Yeah, you could. I mean, you could make this your alcohol and this your alkene, but again, it's gonna, really hinder alcohol trying to attack. Is there any other, maybe using the same alcohol, is there any other alkene we could use?
You would have it at one of the ends.
Yeah, I think, let's see, would that work? Yeah, so the mercury would end up across the double bond, and you get attacked by the alcohol at the more substituted position. So yeah, I think that would work too. Which one is better? Well, I'd say they're roughly the same. My answer to which one is better, I think, would be which one of these alkenes could you make more easily? Because they are pretty much equivalent in terms of their use. All right. Any questions on the synthesis of these ethers?
So for the alcohol that you wanna attach to the first compound, right? Is there any limitations on it, like the tertiary alcohol being a tertiary position, or?
I would probably try to avoid using tertiary alcohols on this reaction. They just end up being very, very slow.
Okay, on paper it's fine.
Yeah, on paper it's fine. But yeah, in practice it would be a painfully slow reaction. Okay, then, so what we've talked about now with the synthesis is you have two really good ways, two complementary ways of making ethers. You have the Williamson ether, which is great for making these unhindered ether products, and then you have the alkoxymercuration, which is good for making the very hindered ethers. So armed with the two of those, you should be able to make virtually any ether that's thrown your direction. Mhm.
So the alkoxy method doesn't work for making unhindered ethers?
Not very well,
Okay.
yeah. Okay, and then let's, oh, by the way, just a word on the Williamson ether synthesis. So I gave you two ways of deprotonating an alcohol up here, either sodium hydride or sodium elemental. By far the more common way of doing that is with sodium hydride. Sodium metal, the elemental sodium, I don't know if you've ever worked with it before, but it is kind of a pain. All of the alkali metals are not really like metals in the traditional sense. They're solid, but they have a consistency of like cold butter. So you can literally take your spatula that you have in your drawer and cut off a piece of the metal. The other thing that complicates their use is they are very, very reactive, and they tend to spontaneously combust in the air. So as a result, they're always stored in mineral oil. So if you want to try to use it, you've got to imagine you've got this jar with the sodium metal that's kind of surrounded by a bunch of mineral oil. So you've got to take your spatula, cut off a slice, probably put it on a paper towel because you got to get all that mineral oil off of it. And then usually, in order to help with that, you spray with some hexane. Because the nonpolar hexane will kind of dissolve the mineral oil. And then you've got to go take that chunk that you just cut off and hope it's the right mass. Put it on a balance, weigh it out. Hopefully you've got the right amount. all the while you're hoping it doesn't spontaneously combust on you. So it's not exactly the easiest or most convenient way of doing things. So sodium hydride, on the other hand, is a nice, well-behaved powder. Weigh it out on the balance, chuck it in the reaction mixture, and you're good to go. So yeah, most people will use sodium hydride for this reaction. Okay, let's look at reactions. Ethers are inert to most things. Which is why they're so commonly used as solvents. You know, if you think about it, you don't want your solvent participating in the reaction. All you want it there to do is just solubilize your reactants. And so ethers are well suited for this purpose because they really don't react with very much. Right? This is why you see we tend to use ethers when you're doing LAH reductions. You tend to use ethers when you're doing Grignard reactions. They just don't react with a lot, right? And so the things that they will not react with are going to be base, nucleophiles, reducing agents, dilute acid,
Professor, you said they react or they don't react with those?
say again, sorry?
Did you say they will react with those?
No, they will not. They are
Oh.
inert to those conditions. So they're pretty stable to most things. In fact, the only thing that you have to worry about are oxidizing agents and strong, hot acid. And I'm not talking about maybe a little sulfuric acid you use to catalyze. Generally, the only thing you have to worry about is hydrobromic and hydroiodic acid. So, I mean, really, nothing but the strongest among the acids are going to do anything to the ether. So I want to talk to you a little bit about those two things. Neither one of these, by the way, is something that you typically set out to do. They're more so just kind of happen by accident. So with the oxidation, for instance, if you have an ether, let's use diethyl ether because it's the most common one. An oxidizing agent, or even just oxygen in the air, will cause these to oxidize. Kind of weird oxidation products. So the first one that I drew, these are called organic peroxides. So you probably remember think back to your Gen Chem ion nomenclature. You probably learned the peroxide ion. Most people notice this from the context of hydrogen peroxide. Hydrogen peroxide is just this oxygen-oxygen bond surrounded by hydrogens. Okay. The only difference here is instead of those hydrogens being attached to the oxygen-oxygen bond, we're attaching alkyl groups. So that's why we call them organic peroxides. The other thing that's here on the right are called hydroperoxides. Nobody really wants to form these because, as it turns out, they are fairly explosive. It's more something you have to be careful of. I don't know if you've ever noticed or not, but if you ever look at an ether bottle, there's a couple things that are kind of unique about them. Number one, they're always small. You're never gonna go into a lab and find like a 4-liter drum of ether. They don't sell them in that quantity for a reason. Ether bottles are always either in brown plastic or they're in metal cans. And that's because light can kind of expedite the oxidation process. So they try to exclude light from the container. They always have an open on date. So anytime you open a bottle of ether, you're always supposed to fill in on the label the date that you opened it. Because you don't want these sitting around for months and months and years. Because over time, the oxygen in the air will oxidize the ether to these explosive oxidation products. And there have been many lab explosions caused by these ether peroxides. This usually happens in labs because most organic chemistry labs have these things that are called stills. And so, for instance, you've got your ether in a still, and it's just a big distillation setup. And the point of them is that it allows you to get very, very dry solvent. Water really causes problems for many, many organic reactions. And so any kind of an organic chemistry lab is always going to have a series of stills set up for all of your common lab solvents. And so if you had an ether still, so by the way, you put sodium typically in here because it helps soak up water. But in any case, you have to heat these and you distill off the ether, and then whenever you collect it over here, you get very, very dry solvent. So the problem is, if you've got ether in the still that's been sitting around for a long time, especially as you start kind of getting low in volume, the still becomes more and more concentrated in these peroxides. And turns out they're quite shock sensitive. So as you start getting to lower and lower volume in the still, if you have a buildup of these peroxides, just a minor kind of nudge of the still can cause them to explode. And what's worse is ether is an incredibly flammable liquid. So you have this explosion that occurs, and then usually a really big fire because of the flammable ether. So it can be quite dangerous. So what they sell anymore, they have these little test strips. So kind of like if you have a pool, you've got little test strips that can test the pool water for pH and various other things. Well, you have these little test strips that will test for peroxide concentration. So before you kick on the still, you take the test strip, dip it in the ether, and make sure you don't have a bunch of peroxides in there that could potentially explode. So again, it's not something this is not a reaction you want to have happen, it's just something to beware of. All right. Any questions on this one? All right, so I think that's probably a good place to stop for today. So I will see you all in about 10 minutes.